Now in this video we'll discuss about Gaussian surface. We already studied Gauss's theorem. The total flux passes through any closed surface is equal to 1 by epsilon 0 times charge enclosed within the surface. So a closed surface is needed for the application of Gauss's theorem, and that particular closed surface where Gauss's theorem can be applied is called Gaussian surface. And a Gaussian surface can have any shape, but it should have certain symmetry with the charge inside. Gaussian surface can have any shape, but some symmetrical approach is taken in order for the easiness of calculation. There are three types of symmetry. The first one is spherical symmetry, second one is line symmetry, and the third one is surface symmetry. Now first we will discuss about spherical symmetry. Spherical symmetry means if the charge is a point charge or any spherical charge distribution, the Gaussian surface should be in the form of a sphere, and that sphere is called Gaussian sphere. Why the Gaussian surface should be in the form of a sphere? This particular charge or a charge distribution produces an electric field. If it is a sphere, I can consider a small elemental area over here, and the area vector will be parallel to electric field. Therefore theta will be 0. So our aim is to find a flux linked with the surface, because Gauss's theorem primarily deals with the flux and charge. Flux linked with the surface phi is equal to integral of E dot ds, where expansion will be like this: E ds cos of theta. Now in these type of Gaussian surface, results of theta is equal to 0. Therefore E ds cos of 0, that will be E ds only. Moreover, electric field due to this charge at any point on the Gaussian surface will be same, because charge remains same, distance also remains same. Therefore electric field E is equal to 1 by 4 pi epsilon 0 q by r square remains same throughout the sphere. Since electric field is a constant, that also can be taken out. E into integral ds we already know, 4 pi r square. So primary purpose of having a spherical Gaussian surface, or generally having a symmetric approach, is to make electric field constant throughout the surface, so that it can be taken out of the integration. So the integration will not be tedious. Now the second one is line symmetry. If the charge inside is in the form of a line with a certain charge given on it, then the Gaussian surface should be in the form of a cylinder, and that particular cylinder is called Gaussian cylinder. And this particular point we will discuss later when we study the applications of Gauss's theorem. And the third symmetry is surface symmetry. Here the charge is given in a sheet of charge. Surface charge distribution is this. At that time, Gaussian surface will be in the form of a pillbox. What is a pillbox? It is nothing but a cylinder only, but the cylinder is not placed vertically up. Instead of that, it is placed horizontally, extending on either side of this particular sheet equally. So this type of cylinder is called a Gaussian pillbox. So as we already discussed, the primary purpose of symmetrical approach is to make this integration easy. Otherwise the surface integration will be tedious, because the electric field will not be constant all over the surface, as well as angle between electric field and area vector will not remain same throughout the surface. Now next property of Gaussian surface is the charge may present inside or outside, but flux contribution is due to the charge present inside only. The charge may present inside as well as outside, but flux contribution is due to the charge present inside only. Let us consider a Gaussian surface of any shape, and certain charge is present in this region. Let q1, q2 and q3 be the charge present in this region. So how much charge is present inside a Gaussian surface? q1 and q2 is the charge present inside the Gaussian surface, and charge q3 is outside. So this particular property says that outer charges will not contribute to the flux. Inner charge only contribute to the flux. these two charges are positive because sign of the charge is not mentioned, then the flux through the Gaussian surface will be, according to the theory we studied, flux phi is equal to 1 by epsilon 0 times charge enclosed. The charge enclosed will be q1 plus q2. The charge may reside inside or outside, but flux contribution due to charge present inside only. The outer charges will never contribute the flux. The next property or point is, if the field lines enters the Gaussian surface, flux is considered as negative. If the field lines leaves the Gaussian surface, flux is considered as positive. This particular concept I will explain. Let us consider a spherical Gaussian surface. Not only spherical Gaussian surface, you can consider any type of Gaussian surface, but no charge is present inside, only a charge present outside. Let this be a positive charge. The positive charge always produces a field radially outwards like this. Now you can see this positive charge enters through the region 1 of the Gaussian surface, and positive charge leaves through the region 2 of the Gaussian surface. Right? Now I'm taking an elemental area on the region 1 of the Gaussian surface as well as region 2 of the Gaussian surface. Now look at the area vector. Here the region 2, the area vector is like this, that and electric field are parallel to each other. Look at area vector on the region 1, electric field is like this, but area vector perpendicular to the area which is taken, and E and ds are 180 degree. Now what is a flux contribution? Phi is equal to E ds cos of 180 in the region 1. That means cos of 180 is equal to minus 1. Therefore phi 1 is equal to minus of E ds. If the field lines enters, the flux contribution is negative. That is what we written here. If the field lines enters the Gaussian surface, flux is negative. So here the field lines are entering, the flux is negative. So that we proved like this. Now here in the region 2, you can see phi 2 is equal to E ds cos of 0 because there is no angle between E and ds. Therefore phi 2 is equal to E ds, that is positive. So that means if the field lines leaves the Gaussian surface, flux is considered as positive. So this particular charge produces certain flux in this particular Gaussian surface. Now what is a net flux? The net flux due to this particular charge is given by phi is equal to phi 1 plus phi 2. Now what is phi 1? Minus E ds. And what is phi 2? E ds. So phi is equal to minus E ds plus E ds, that will be 0. Charge may present inside or outside, but outer charges will never produce flux. If a charge is present inside, you can see here this particular positive charge present inside, and it will produce an outward flux only. So that means the field lines due to this is cutting through the surface and going radially outside. That means the field lines are leaving the surface. If the field lines are leaving the surface, the flux is considered as positive. So that means this particular charge which is present inside, if it is positive, that produces a positive flux. On other hand, here you can see a negative charge is there. Obviously we already studied that negative charges, the field lines are radially inwards. If I'm constructing a Gaussian surface around, you can see field lines are entering. We already studied here, if the field lines are entering the surface, then the flux is negative. So a negative charge will always produces a negative flux in this Gaussian surface. Let us study some of the applications of Gauss's theorem. The first one is electric field due to a point charge. Electric field due to a point charge we already studied. The equation for electric field due to a point charge is equal to 1 by 4 pi epsilon 0 q by r square, and that equation we are going to derive. For that, let us consider a point charge placed in air or free space, and at a point P we have to find out electric field at a distance r from the center. In order to apply Gauss's theorem, let us construct a Gaussian sphere, because the charge present inside is spherical in shape, so the Gaussian surface should be spherical in shape. And I am constructing a Gaussian sphere of radius r. I am just showing the part of the sphere only. After constructing a Gaussian sphere, I have to take an elemental area ds. This is a positive charge and that produces an electric field radially outwards. This is the direction of electric field. Area vector is always perpendicular to the area. So you can see E and ds are parallel to each other. When E and ds are parallel to each other, theta is equal to 0. Now in this situation, we can apply Gauss's theorem. The Gauss's theorem, we already studied that phi is equal to integral of E dot ds is equal to q by epsilon 0. The flux passes through any closed surface is the surface integral of electric field over that surface, that must be equal to 1 by epsilon 0 times charge enclosed. But here E dot ds can be written as E ds cos of theta. Theta is equal to 0. We already discussed. Therefore, it will be E ds cos of 0 is equal to q by epsilon 0. Cos of 0 is equal to 1. Therefore, integral of E ds is equal to q by epsilon 0. Now, the next point is E is same everywhere on the Gaussian sphere, because the radius remains same and the distance of the points, any point on the sphere from the charge remains same. Therefore, E remains same everywhere on the Gaussian sphere. Since E remains same, it can be taken out. So E into integral ds is equal to q by epsilon 0. Put as equation number 1. Now we know that integral ds is equal to 4 pi r square, where integral ds is the total surface area of the entire sphere, that will be 4 pi r square. Put as equation number 2. Now substitute 2 in 1, we will be getting E into 4 pi r square is equal to q by epsilon 0. Therefore E is equal to 1 by 4, take this particular 4 pi r square to the denominator, it will be 1 by 4 pi epsilon 0 q by r square. In terms of vector, I can write E is equal to 1 by 4 pi epsilon 0 q by r square into unit vector r. Now sometimes questions may come like this also. Deduce Coulomb's law from Gauss's theorem. If the question comes like this, the steps remain same up to this particular point. So up to this particular point, what we calculated is electric field at this point P due to this particular charge. So we already calculated electric field at this point P due to this particular charge by applying Gauss's theorem. Now I am going to place another charge Q0 at this point P. Now the charge Q0 experiences a force. We already studied F is equal to Q0 times E. Whenever a charge placed inside an electric field, it experiences a force F is equal to Q into E. Here the charge is Q0, therefore Q0 times E. And E is already given 1 by 4 pi epsilon 0 q by r square into unit vector r. I can substitute, therefore F is equal to Q0 times 1 by 4 pi epsilon 0 q by r square into unit vector r. That means F is equal to 1 by 4 pi epsilon 0 q0 divided by r square into unit vector r. This is nothing but Coulomb's law of electrostatic force between two charges.